Okay, hello everyone. Today we'll be doing elementary mathematics. Okay, on the topic indices and standard form. Okay, some schools they may not begin with this topic. They may begin with quadratic equations, but usually they'll start with indices and standard form. Okay, so we'll just go into indices now. So what are indices, right? Basically, indices, what it means is just basically the power of a number. Okay, so if you actually look at the general form, okay, if you have a number a, okay, and you multiply a by itself by n times, okay, so a times a times a, you do that n times, right? You can actually express that as a to the power of n. Okay, so maybe let's just look at an example. Okay, so if, for example, if a is a number 2, right, and you multiply 2 by itself 5 times 2 times 2 times 2 times 2, it's the same as actually 2 to the power of 5, right? That's what we are we already know. Okay, but it's just here they just call it differently. They just define it as, instead of having a number 2, they generalize it and say any number n, any number a, okay, and you multiply itself, instead of saying that it's 5 times, they say n times, right? So what you get is basically a to the power of n, okay, which is the same as 2 to the power of 5, right? So in this form, a to the power of n, okay, is actually called the index notation. Okay, over here, index notation. Okay, whereby a is called the base and n is called the index of power. So index is the same meaning as power. Okay, so yeah, that's just how it is named, right? And now let's go on to this is the more important portion. Okay, the laws of indices, right? So you will have to remember, okay, all of these different rules of which you can actually manipulate indices, right? So I understand that a lot of you may have difficulty remembering, so shortly I'll be going into how do you actually prove or derive them. Hopefully that will help you to remember better, but for now let's just take a look at what are the laws of the indices. So the most fundamental formula will be a to the power of m. If you multiply it by a to the power of n, what you get is a to the power of m plus n. Okay, so what happens is that you can think about it this way. Okay, if you have the same base, okay, the same base a, okay, if both indices or index notations have the same base, you can actually combine them. Okay, as you can see, the base is a, okay, because you've actually combined them. Okay, and in doing so, okay, what happens to the power or index? You add them up, right? So if it's multiply, okay, the indexes add them up, so it becomes m plus n. Okay, so if they have the same base, you can combine. Okay, and what happens to the index? The index, you add the indexes. Okay, so an example will be 2 to the power of 3 times 2 to the power of 2, because they have the same base of 2. Okay, you can actually combine them. Okay, so same base of 2, you combine them, and what happens to power? You add them up, 3 plus 2, you get 5. Alright, so that is the more commonly used rule, okay, in indices. The second one will just be the opposite, right? So same thing, same base a, okay, but just that if it's divide, okay, it will be m minus n. So if it's times, you add the indices together. If it's divide, you subtract the indices. Okay, so 1 and 2 is pretty much they are linked. Okay, you don't really have to spend extra effort trying to remember number 2, because it is sort of an extension of 1. Right, so if I have 5 to the power of 3 divided by 5, very important, the same base, so you can actually combine them, right? So it goes to 5 to the power of 3 minus 2, because it's divide, so you get 5 to the power of 1 equals to 5. Right, so think about it in terms of you're able to combine them because you actually have the same base of 5, right? Okay, yeah. Okay, I'll not do any underlining on 2 because I just want you all to know that 2 can be derived from 1, so don't really have to stress too much about the second formula. For part 3, if I have Okay, this is slightly different from 1 and 2. Okay, so 1 and 2 is basically when you actually have two different index notations and you are multiplying or dividing them. Whereas, as you can see, I underlined AM and AN. They are two different, okay, sets of index notations. Whereas in number 3, formula 3, you only have a single one, okay, which is just a to the power of n, right? You don't have two of them, you just have one of them. But what happens is that you actually apply a power, right? So in 1 and 2, you're actually doing a multiplication or a division. Whereas in rule 3, you actually apply a power to the index notation, right? So just one index notation and you apply a power to it, right? When you apply a power to it, so for example, you have a to the power m, and on top of that, you apply a power n to a to the power m, okay? You can actually say that it is a to the power of m times n. So the index notations, okay, for the in terms of the indexes, they will actually multiply each other, okay? So for example, if I have 2 to the power of 3 and I square 2 to the power of 3, okay, apply a power 2 to this index notation, the indexes will multiply. Okay, so it's 3 times 2, that will give me 6. Okay, so rule 4, okay, rule 4 is and 5, they are actually very similar, okay, they are actually related, and you can sort of see them as related to rules 1 and 2 as well, in the sense that in rules 1 and 2, the bases are the same, therefore you can combine them. But in rules 4, for example, the bases are different, but it is the power that is the same, right? Okay, as you can see, it is the powers that are the same, right? A, M, and B, M, okay, A to the power M, B to the power M, both of them have the same power of M. So if you have something that is the same, okay, be it the base or the power, you can actually combine them together. Okay, so here in this case, you have the same power. How do you combine them? Okay, so you just have the M on the outside and you just say is A times B to the power of M. Right, so you put a bracket over A times B. Collectively, they are both to the power of M. So an example will be 2 to the power of 3 times 5 to the power of 3. That will be 2 times 5 to the power of 3. Okay. So very important, you cannot combine unless you have something in common. So rules 1 and 2, you have a common base. Rules 4 and 5, you have a common power. Okay, so when you have either one of them that's common, you can actually combine them. So rule 5 is just if it's divide, okay, AM divided by BM, you can combine them. So it's just A divided by B to power of M. Okay, because here's a divide, so within the bracket it will be A divided by B. So rules 4 and 5 are related. Okay. So rule 6 is basically something that is just you can see it's quite straightforward. Okay, anything to the power of 0 is equals to 1, right? So A can be any number. Okay, A can be 3. For example, if we look at the example, A can be 3. A can be half. A can be 100. Doesn't matter what the number is, as long as the power is 0. Okay, this whole term will just be equals to 1. Okay, so anything that is to the power of 0, it will give you the answer of 1. Okay, rule 7. Okay, rule 7 basically states that if you have a negative, okay, here as you can see is negative n. Okay, so is instead of having, previously we were all dealing with positive indexes, right, or positive powers. Here the power or index is negative. So what do you do about the negative, right? You can actually, the negative is actually the same as 1 over. Okay, it is sort of the inverse of the original, which is A to the power of n. Inverse just means 1 over, right? So how do I like to see is that I just take this line over here, this negative sign, okay, I bring it up on top of this whole term. Okay, so after I shift this negative up, what remains is A to the power of n, and this negative line I'll just extend the whole line and it becomes a divide, and it's just 1 over, right? So I repeat, I take this negative sign, I bring it on top, so what remains is just A to the power of n. On top, I extend this whole line, and it's just a 1 over A to the power of n. Okay, so if you have a negative, okay, it basically just means it's the 1 over. Okay, I repeat, negative power means 1 over. Okay. So an example will be if I have 4 to the power of minus 2, I bring this negative up, okay, extend the line, it will be 1 over 4 to the power of 2. Right? Okay, now what about this? Okay, this 1 over a to the power of minus n equals to a to the power of n, right? Okay. Basically, if I have a, so I'm talking about this now, if I have a 1 over a to the power of minus n, correct? This 1 over will cancel away the negative. Okay, this 1 over, if the denominator is a negative power, it will cancel away the negative to just give me back the a to the power of n. Why? Because I'm doing a double inverse, right? Here, a to the power minus n is the inverse of a to the power n. If I take the inverse of the inverse of a to the power of n, I'm just left with a to the power of n. Okay, I repeat. Here, I'm taking the inverse of the inverse of a to the power of n. So I'm just left the inverse, and the inverse will cancel out. So I'm just left with a to the power of n. Alright? So, an example will be if I have 1 over 3 to the power of minus 2, okay, the 1 over will just cancel away the negative, and it will just give me a 3 to the power of 2, and that will be 9, okay. So I would say that this actually is you actually it's not that difficult. After a while, you actually see that it is actually quite you'll be able to understand it better once you're more comfortable dealing with fractional sort of fractions involving power, okay, involving index notations. Okay, this will become quite second nature to you. Okay, so what about number 8? Okay, if I have a over b to the power minus n, what happens, right? Okay, it is actually this negative, you can actually see as you are flipping around whatever that's within the bracket. Okay, so it becomes b over a to the power of n. Alright, okay, so I will go more in depth into why this actually is the case shortly, but you just have to understand that for now, that if there's a negative sign, you are actually taking the inverse. So it is the same principle as 7. Okay, so actually 7 and 8, they also link. Okay, if I have a negative sign, negative power, okay, just like in 7, a negative power, I'm actually taking the inverse. Okay, so I'll just write inverse here. Okay, inverse just means that it is 1 over of the original. Okay, inverse just means that it is 1 over of the original. Okay, so in this case, if I take 1 over of the original, which is, so the original number is a over b. If I take 1 over of a over b, it's actually b over a. Correct? I'm just flipping around the fraction. I repeat, if I have 1 a over b to the power minus n is actually the inverse of a over b. Okay, and then because it's a negative sign, so it's the inverse, and then what I do if it's the inverse of 1 a over b is that I flip the a over b, just like how a, if I flip it around, it becomes 1 over a. Okay, here a over b, I flip it around, it becomes b over a. Okay, and the negative sign basically it becomes the inverse, and I'm left with b over a to the power of n. Right? Okay, so inverse means 1 over something. Okay, so that's what inverse means. Alright, so an example will be if I have 2/3 to the power of minus 2, okay, the negative will just be the negative power, okay, will just be an inverse. Will just mean that it's an inverse, so it's just I just flip the fraction around, becomes 3 over 2 square. Alright. Okay, so now I'll go to number 9. 9 is a to the power of 1 over n equals to you call this root n. Okay, so a root n of a. Okay, so so for example, if okay, this is actually it may seem complicated, but actually if you think about it logically, okay, if you have 16 to the power of half, right? We all know that half represents square root, right? This one is something that we have learned in lower secondary. So half represents square root, 1/3 represents cube root. So if I have half, it's actually square root. Okay, so actually there's a 2 here, but because it is a square root, we usually don't write the 2 there. Okay, but 16 to the power half is actually square root 16, right? The half is actually a square root. When I have a 1 over, it actually means that it is square root of that of that number. Okay, depending on what the root is determined by the number at the bottom, right? So it's 1 over 3, it is cube root, right? So this number here determines at the bottom, this number at the bottom determines how much of the root is it, right? So in this case is 2. So what this means in the general form is that if I have any number to the power of 1 over, because it's a 1 over, it represents it's a root, okay? And this number at the bottom here will tell me what the root is. So it's root, okay, n, right? Because the number here is n, so it is root n. So 1 over represents is a root, and the degree of the root will be determined by a number at the bottom, which is n. So for number 10, the final rule, okay, actually 9 and 10 are actually related. Okay, so why is that so? Because if I have, for example, if I take a look at a to the power of m over n, right? So if I have the root n over here, okay, what this means is that it is the same as a root n, correct? So if you can see this a root n over here, it is the same as this a root n over here, right? Alright, and on top of that, what I do is because it is to the power of m on top of the numerator, so there's an extra m that is a power of this a to the power root n, right? There's extra power m here. Okay, and what happens is that if I have in this form, I can actually just bring in this m, I can actually just bring it into the bracket here as well. Okay, it doesn't matter whether this m is outside of the bracket or is within the square root. Okay, it has the same mathematical value. Alright, so an example will be if I have 8 to the power of 2/3, okay, I can apply the 1/3 as a cube root of 8, and I can do the square of everything, or okay, this square can be expressed as within the bracket as well, doesn't matter. Okay, so yeah, that will be all the rules that you have to remember. Alright.